These pictures remind me of my first job working as a janitor. What we see is a person stripping the floor. So normally a floor has wax on it, and that wax occasionally gets to the point where it's no good anymore and you need to remove it. So what you do is you get a chemical stripper, you pour it in the mop bucket, and then you slosh it around on the floor with the mop. And now you're standing in water while walking this floor machine back and forth. You lift up the handle, it goes one way, and you push down ever so gently, it goes the other. And back and forth you go while standing in the water. Did I mention the water? Let's draw a circuit and see if we can make some sense of this. So normally we have a switch, then we have our motor. I'm just going to draw it as a circle with an M in it. Right? And this is the hot wire, so that's 120 volts AC, and this is the neutral wire. You could think of that as the return. Now there is another wire that's typically associated with these machines. We'll draw that in green, and that is the ground wire. The ground wire is a safety device that is attached firmly to all the exposed metal on the machine. Under normal conditions, that ground wire doesn't do anything at all because the current will flow from the hot through the switch, through the motor, and back through the return. There's no current in the ground wire. However, if the machine develops a fault, let's assume a worst case fault where 120 volts connects directly onto that ground. Well, now we've got a problem because you are out here and you are in contact with that machine, right? You're holding on to the handles. And again, I mentioned the water. You're standing in water, which is probably not where you want to be if this thing has a hot to ground fault. This has just become a parallel circuit where we have some resistance here in the hot wire. We have the ground wire, so that's this resistance here. And then there's the part that you really care about, and that's you. So R of your body. You might have a resistance on the order of 500 ohms. You're going to hope that this resistance is small enough so that the current through you does not reach a dangerous level. My name is Aaron Dolan, and I'd like to talk to you about two things today. One is the voltage divider circuit, and the other is the current divider circuit for circuits such as we see here. In our previous lecture, we looked at a circuit that looked like this. To solve this problem, we started by drawing a box around these parallel connected resistors. We calculated the resistance of that box as 1 over R box is equal to 1 over 2 plus 1 over 6. So the resistance of the box, 2 inverse plus 6 inverse equals inverse, was 1.5 ohms. And if we were to redraw this circuit, we would see our 7 volts, our 2 ohms, and then our 1.5 ohm. So this is our original R1, this is R box, and we said that was 1.5 ohms. We could have gone on from there. We could have calculated the R total. So R total is 2 plus 1.5, giving us an R total of 3.5 ohms. You might have calculated the current at that point. So we have a current flowing in this direction. So your current is a voltage divided by a resistance. which is 7 volts. It was 7, right? Yep, 7 volts, 7 volts. 7 volts divided by 3.5 ohms gave us 2 amps. If we go back up to our original circuit, that means there is a 2 amp current flow in that direction. That certainly helps, but we're still left with a few questions. For example, what is the voltage here? What is the current passing through that resistor? And what is the current passing through that resistor? So let's go back to this step here from our example. We said 7 volts. We had an R1 of 2 ohms. We had an R box of 1.5 ohms. If we wanted to calculate the voltage on R1, we would take the current, which we just calculated, right? We said that was 2 amps. We would say the voltage on R1 is equal to 2 times 2. Right, so we're looking for a voltage, so we cover that up. We say a voltage is a current times a resistance. And we said the current was 2 amps and the resistance was 2 ohms. So that gives us 4 volts. The resistor, correction, if we were curious about the voltage on the box, we would calculate that as I, which is 2 amps, by 1.5 ohms, which gives us 3 volts. And then, if we took the sum of those, that would give us 7 volts DC. By the way, you remember what kind of statement that is? That is KVL. The sum of the voltages in a closed loop is equal to 0. Okay. So again, that was a two-step process. We had to go up here. We had to simplify the circuit a little bit. Then we had to calculate the current. Once we knew the current, we could come and calculate the voltage across R1 or across R box. And you'll see R box here is a representation of R2 and R3. So the voltage on R2 would be that 3 volts, and the voltage on R3 would also be 3 volts. Again, you can see that they are on the same node. Okay, again, that was a two-step process. We can do it in one step. So here is the equation, and I'll show you the derivation in a moment here. So the voltage of interest is equal to the resistor of interest over the total resistance multiplied by the source voltage. So we say this is the resistor of interest. This is the total series resistance. This is the source voltage. And this is the voltage of interest. We'll put that to use in this circuit. Let that be 5 ohms, 15 ohms, and 20 ohms. We want to find the voltage on R2. Using the voltage divider, we would say that the voltage on R2, because that's the one we're interested in, right? Voltage on X, is equal to the resistor of interest, in this case 15, over the total resistance, which is 5 plus 15 plus 20, multiplied by the source voltage. So the voltage on R2, let's see if we can figure that out. So what do we got? We got 15 divided by 5 plus 15 plus 20 equals multiplied by 100 equals, which gives us 37.5 volts DC. Okay, we did it in one step. Remember before, it was a two-step process. With our previous tools, we'd have to calculate this current first. Now we don't need to do that. We can go directly to the voltage without that intermediate step. I'm going to walk off to the side of the screen and show you how we derived the voltage divider equation. Let's start with a circuit, and let's pay really close attention to only one of the resistors. From Ohm's law, we can make some statements about this resistor. We would say the voltage of interest is equal to a current by resistance. And we only considered this piece right there. If we step back and we consider the entire circuit, we know there's a current flowing in here. We could say that that current is equal to the source voltage, right, Vs, divided by R total. This leaves us with two equations. We have one equation describing just the resistor piece that interests us, and then we have another equation describing the greater circuit. But you'll notice that the current through our resistor of interest, right, this current right here, is the same as the total current. Therefore, we can substitute this piece in. And when we do that, we see that the voltage of interest is equal to the source voltage over the total resistance, and that is multiplied by the resistor of interest. And now if we just do a swap here, the voltage of interest is the resistor of interest over R total multiplied by Vs. I hope that was useful. That's one way to think about the voltage divider equation. Either way, you'll definitely want to go back and write this on your note card because it's a very useful circuit. Let's go back and apply it to our original circuit. So here's an example. Here's that 7-volt DC supply. There is your R1 and R2 of 2 ohms and R3 of 6 ohms. As before, we start out by putting this piece into a box where our box is 2 in parallel with 6. We've solved that already. Our box is equal to 1.5. Redrawing the circuit if you like. Where this is R1, 2 ohms, our box, 1.5 ohms. And now we want to know the voltage on the box. Okay, so the voltage on the box is equal to the resistor of interest, which is the resistance of the box, over R total, which means it's 1.5 over 2 plus 1.5. So there's where our 2 came from, and there's our 1.5, and all that's multiplied by source. So the voltage on the box is equal to 3 volts DC. So that means we have 3 volts DC here, or if you prefer, the voltage here is 3 volts DC. While we're here, we may as well calculate the current on R2. The current on R2 is equal to, let's look, cover up method. What is a current? A current is a voltage divided by a resistance. So it's 3 divided by 2. And the current on R3 is 3 divided by 6. So that's 1.5 amps and 1/2 an amp. If we add them together, we would see that that is 2 amps. So if we put that here in our circuit, if we put an ammeter there and an ammeter there, it would read 1.5 and it would read 2. By the way, this statement here, remember what that was? That is an application of Kirchhoff's current law, the summation of currents. Let's talk about the current divider. The current of interest is equal to the total resistance over the resistor of interest multiplied by the source current. So current of interest, we said this was the total parallel resistance. This was the resistor of interest, and this was the source current. Something to notice, the current divider, we use the word parallel. If we scroll up a little bit, when we go to the voltage divider, we see the word series. So the voltage divider works on series circuits, and the current divider works on parallel circuits. Let's work a quick example. So suppose this is 10 amps, and we have 3 resistors.
We have an R1, R2, and 3 ohms, 9 ohms, and 18 ohms.
With the tools we have now, we would first need to calculate the total resistance of the circuit, right? What is the total parallel component? We would then need to calculate the voltage, and then once we knew the voltage, we'd have to calculate the current for an individual resistor. That's a two-step process. Again, calculate the voltage and then calculate the current. With the current divider rule, you can do it in one step. You still need to calculate the total resistance of this piece. We're going to call that 1 over R parallel is equal to 1 over 3 plus 1 over 9 plus 1 over 18. So the parallel component piece, 3, 9 inverse, 18 inverse equals inverse equals. So that works out to be 2 ohms. So now we go back to our current divider equation and see if we have everything we need. Let's suppose we are looking for the current through R2. Okay, so R2 would be a resistor of interest. Do we have the total parallel resistance? And the answer is, well, yes, that's right here. And do we have the source current? Yes, that's this. So we have enough information that we can do this calculation. We would say that the current through R2 is equal to R total, which is the parallel piece, over the resistor of interest multiplied by the source current. So R2 is equal to 2, right, that's this one, over 9 multiplied by 10. So the current on R2 is equal to about 2.2 amps. 2 divided by 9 equals times 10 equals about 2.2 amps. Like we did before, we're going to step off to the side of the screen and we're going to show the derivation for the current divider. We start with a circuit. We'll do the same thing we did before. We will focus in on a particular resistor of interest. And what we want to know is what is the current. That current of interest, is the source voltage divided by the resistor of interest. Come back here. We say a current is a voltage divided by that resistance. Okay, so that was the small circuit. Now we're going to look at the larger circuit that fits within. Here we could say that the voltage, right, the source voltage, is equal to the source current by the total resistance. Imagine you had a current meter right here. So we could talk about this source voltage. Right? Do the cover-up method of voltage is a current times a resistance. So it's this current flowing through this amp meter and all this resistance here. As we did before, we're going to do a substitution now. We would say that the current of interest is equal to the source current multiplied total resistance over the resistor of interest. And if we flip this around just a little bit, we could say that it's R total over the resistor of interest multiplied by the source current. So that is how you do the derivation for the current divider. Before we finish, I wanted to show you a common error that people make. It goes something like this. This common error involves the English language of all things. We use the word total, and we have to be very careful about what we're talking about. We could talk about the total resistance of this circuit. That total resistance, R total, is equal to 3 plus 4 in parallel with 12 in parallel with 8. And when we solve for that, we end up with 4 inverse plus 12 inverse plus 8 inverse equals inverse. And then we have to add 3. So we end up with a total resistance of 5.18 ohms. Again, that's everything, R1, R2, R3, and R4. When we go up to our current divider, you'll notice that there's a T there for R total. But watch out, it's for the total parallel piece. If we come back down here, the parallel piece does not include R1. Okay? The parallel piece, if we're going to do a current divider, does not include R1. So this is the parallel piece when we're talking about the current divider, R parallel. And that is equal to 4 in parallel with 12 in parallel with 8. I think we calculated it already, but let's do it again real quick. So 4 inverse plus 12 inverse plus 8 inverse equals inverse. So that's 2.18 ohms. And those are not the same thing. 2.18 does not equal 5.14. And if you forget that and you use the wrong total, you're going to be in trouble with your problem. For this particular problem, say we wanted to know the current through R3. Right? So what is IR3? Let's try that out. So the current of R3, so that's the current of interest, is R total over Rx by the current source. Now be careful, which total are we talking about? For the current divider, it's the piece that's circled right here. It's the total parallel piece. So that's our 2.18 ohms over Rx. We said that was R3, so that's 12 multiplied by the source. By the way, be careful with this. You see this 2 amps? That 2 amps is flowing through R1. And if you want to be fussy, we don't even care what the value of R1 is, because this current divider will do whatever is necessary to make sure that there will be 2 amps flowing through this part of the circuit as well. Right? So if we were to put an amp meter there, we would see 2 amps in that direction. Anyway, solving for this current, we end up with 2.18 divided by 12 equals times 2. Our current is 360 milliamps. Well, that's all I had for today. Let's do a quick review, and then we'll call it a night. So we started out by introducing the voltage divider. And we said the voltage divider is to be used with series circuits. So the voltage divider, you could figure out the voltage on any resistor of your choice. And the voltage divider is really nice because it takes what was a two-step process and makes it a one-step process. We showed an example, and then we introduced the current divider. We said the current divider was used for parallel circuits. So given resistors in parallel, you can calculate the current through any one. Again, it takes a two-step process and converts it to a one-step process. The derivation for both the voltage divider and current divider was shown off to the side. We showed this by first focusing in on a small part of the circuit and then the larger part of the circuit and doing a substitution for current. We did something very similar for the current divider. We focused in on a small part of the circuit, we came up with an equation, then we focused in on the larger part of the circuit, came up with another equation, and then performed a substitution. We ended on a cautionary note where I said to be very careful what you mean by the word total. There is the total resistance of the circuit, which in this case includes all of the resistors, and then there is the total parallel piece. It's very important that when you run the current divider that you use the parallel piece and not the total resistance of the circuit. When you come back next time, we'll look at mesh and nodal analysis. Until then, be safe.